Hey everybody, by the end of this video you'll be able to define what a buffer is and then be able to do some calculations pertaining to buffers and even use the Henderson-Hasselbalch Equation to calculate Ka or pH. Now, we need to understand what a buffer is to begin with. One of the previous videos that we talked about, we talked about something called the common ion effect. Okay. Now, the common ion effect creates what we call a buffer. And a buffer is a mixture of a weak, either acid or base, and its conjugate. So for something like ammonia, and so this here is a buffer solution because it's the weak thing, in this case, weak base, with its conjugate. Or if you have acetic acid, okay, it's acetic acid mixed with acetate ion, CH3O2 minus. Okay, this mixture is a buffer solution. And it doesn't have to be these two things in particular. It could be any mixture of a weak component and its conjugate. Okay, these just happen to be two common examples. The beauty of a buffer is that it will resist pH changes as you add acids or bases to it. And this is because there is this ratio of weak to conjugate there. Hopefully I'll get into some of the chemistry behind it. But buffers are very resistant to pH change, and that's important. Okay, one of the real-life examples that I always use, and actually I didn't understand why buffers were a thing, meaning why they were chemically relevant, until I asked the question, I think it was my junior year of college. I said, so what? Why do we care about buffers? And my professor, Dr. Bentz, he looked at me and he said, well, think about your blood. And I said, so? He said, blood is a natural buffer, and it needs to be because if your pH changes too much, you're going to affect the biology of what the heck is going on. So if we can't control the pH of when we add things to our system, then we're going to get completely out of whack, and it's just a bad news. So ever since then, that's when I understood why it's important, in some cases, to control the pH of a reaction. And so buffers allow us to do that. Okay, so let's see what we can do here. Let's move along. So I'm going to move on here, and we will let's talk about this. Okay, now this is the Henderson-Hasselbalch equation. This is where it comes from. But let's talk a little bit about this guy right here. Oops. Okay, and so that equation was pKa equals pH minus the log of the base over the log over the acid. Okay. Now, where does that come from? Well, what I'm going to do, let's see, let me just go back here. Okay. If we look, okay, where this comes from, watch what I do here. Whoop. Okay. Let me delog all of this stuff. Okay. So that's not the official term, but that's what I'm going to say. I'm going to delog it. So I get this plus the concentration of the hydrogen ion, which we know is hydronium ion, times the A minus over concentration of HA. So this is just a rewrite of the equilibrium constant. Okay, and then we go through another iteration, and by doing that, we get to the Henderson-Hasselbalch equation. Okay, we move this and this, and when we switch those, it becomes the Henderson-Hasselbalch equation. Okay, and that's cool because that Henderson-Hasselbalch equation gets us to a place where we can very easily calculate the pH without going through the ICE chart. But this brings up something very important. Okay, let me just rewrite this based on like it were. So this is going to come down here. So let's say we have the pH equals pKa plus the log of the concentration of the acid, I'm sorry, the base, the conjugate, over concentration of HA. Now, right, the point here is the pH is dependent on this ratio right here. The pH is dependent on this ratio right there. pKa is never going to change. So because that's never going to change, what the pH is dependent on of the buffer is really how much acid, how much conjugate acid, how much base there is in the, or how much conjugate base, let me make sure I say this correctly, and then how much acid there is. Okay. We can control the pH of the buffer based on how much conjugate base, this is the con base, and how much weak acid there is. Okay? And so by adjusting this ratio, that can control the pH. Okay? And that's what the Henderson-Hasselbalch equation does. It allows us to show how this ratio here of conjugate base to weak acid controls the pH. So we can use ICE charts to do this. It's not any different. The Henderson-Hasselbalch is a shortcut. Okay, so let's actually look at the problem in here, and we will do this. So it says, what is the pH of a buffer, point lactic acid and sodium lactate? Okay, so we got 0.12 molar lactic acid and 0.1 molar sodium lactate. Okay, so let me clear this off, and this is an example problem. Okay, so your 0.12 molar HC3H5O3. Let me double check that that's right. Okay, and then 0.1 molar sodium lactate. So 0.10 molar NaC3H5O3. Okay, so we want to know what the pH of the solution is. Let's just double check that that's what it is. It's and then it gives us a Ka. Okay, so let's solve this both ways so that you can see that the Henderson-Hasselbalch equation is really just a shortcut. Okay, 1.4 times 10 to the minus 4. Okay, Ka equals 1.4 times 10 to the minus 4. Okay. So, here we go. This is a weak acid problem. So anytime we have a weak acid problem, if we want to solve this, if we forget that even the Henderson-Hasselbalch equation even exists, we would solve this and we would use just what we know about weak acid equilibrium. Okay, so the weak acid equilibrium problem would be HC3H5O3 plus H2O is in equilibrium with H3O plus C3H5O3 minus. And I get it, you're wondering, you're saying, hey Walsh, where does this come in? Well, remember that sodium, all compounds with sodium in it are 100% ionized. So this and this are the same thing. Okay, so now this becomes kind of like a common ion problem. Make our columns. ICE. So what's the initial concentration here? 0.10, 0.12. Water doesn't matter because it's a liquid. Now H3O plus is 0, and now this is 0.10, because again, the lactate ion comes from the sodium lactate. This is completely ionized. So this has a concentration equal to what the concentration is of the solution here. So now we always shift to the side that has a 0. So we do minus x plus x plus x. And again, we're trying to find the pH, 0.12 minus x, x, and 0.10 plus x. So now we do Ka equals the concentration of H3O plus its concentration of 0.10 plus x all over 0.12 minus x. And when we do that, we assume the x is teeny tiny, okay? And by doing that now, we math it, okay? So 1.4 times 10 to the minus 4 equals x times 0.1 over 0.12. Okay, so now we do some math. I'll clear out, my buffers are cool, and we go, let's see here, 1.4 times 10 to the minus 4 times 0.12 divided by 0.1, and you get that x equals 1.68 times 10 to the minus 4. Great. We're not done yet because we have to find the pH. pH equals the negative log of the concentration of the hydronium ion, which in this case, X is the concentration of the hydronium ion. Okay, so pH equals negative log of 1.68 times 10 to the minus 4. Okay, so now we do negative log of that answer, and you get that the pH equals 3.77. Okay, cool, right? It is just a weak acid equilibrium problem with a common ion. Okay, now we can take the same problem, and actually, that's what I'm going to do. I'm going to go up here, I'm going to box this guy, all this, I'm going to go edit, copy, edit, copy, go here, next page, edit, paste. So now it's the same problem, okay? But now we're going to use the Henderson-Hasselbalch equation where pH equals pKa plus the log of the ratio of the base A minus over HA. Okay. So pKa now. What's the pKa? Well, pKa is equal to the negative log of 1.4 times 10 to the minus 4. So the negative log of 1.4 times 10 to the minus 4 is equal to 3.85 plus the log of the A minus. This is the A minus 0.1 over HA 0.12. Okay, so 0.1 divided by 0.12 is 0.833. And then we do the log of that, and so we get that pH equals 3.85 plus a negative 0.079, and so then we do that, 3.85 plus that, and we get that the pH equals 3.77. Now we go back and look. what we had over here. Okay, pH is 3.77. Here, pH is 3.77. So again, the Henderson-Hasselbalch equation is kind of a shortcut instead of going through the weak acid equilibrium type of problem. Okay, so hopefully that clears up some Henderson-Hasselbalch issues, and have a great time.